Hi, everyone. Happy Wednesday to all of you. Hope you're all having a fantastic week. My week is going pretty good. In this video, I just want to touch on a new topic that we're covering for the first time in my Calculus 2 class. We also covered that in my previous calc class I taught, Calc BC, but I thought that this is such an important topic, and not only that, it's really kind of difficult if you're learning this for the first time. A lot of people struggle with this topic when they're seeing it for the very first time, so I thought it would be really good to make a video to kind of help my students in my class understand this concept a little bit better and how the overall process works. So this topic is called integration by parts. It's one of the many, many techniques we're going to be learning in this Calculus 2 class that touch on how to solve a wide variety of different integrals. And after we learn all these techniques, I'm going to have a really specialized section that isn't from the book. It's kind of something I'm creating myself that focuses on strategizing for integration. It focuses on looking at particular types of integrals and kind of just picking up clues and deciding what techniques you have to use. So for example, looking at a particular integral and saying, oh, this has an inner function, it has an outer function, there's the derivative of the outer function, it has to be integration by substitution for this one. So it's a skill that I really, really want my students to have mastered by the time they finish my class. I want them to be able to look at any type of integral and have a really good sense and a really good intuition about what tools they need in order to solve the integral. So by this point, we don't really have any tools to help us with this one we have before us. We're trying to integrate x times cosine of x. So we're going to need a new technique called integration by parts. And in the last video, I mentioned the fact that a lot of the integration techniques can be thought of as opposites of differentiation techniques. They can be thought of opposites of different techniques we use to take derivatives of functions. So for example, in the last video, remember that the integration equivalent of the chain rule for derivatives would be integration by substitution, also called U substitution. So U substitution is kind of the opposite of the chain rule for derivatives. So the chain rule is used for derivatives, U substitution is used for integrals. They have that opposite relationship going. And then integration by parts can be thought of as the integral equivalent, or I guess you could say it's the inverse of the product rule for derivatives. So we're going to take a quick look at the derivation of this rule to help us have a really, really good, solid understanding of why things work the way they do in this new technique we're learning right now. So what if we're trying to take the derivative of x times sine of x? And we know that it's just a simple product. We have a variable times a function. So we can see that the derivative would be pretty simple. We have that product rule for derivatives that tell us whenever we're trying to take the derivative of the product of two different things, it goes like this. We're going to take the derivative of the first factor times the second. So it's going to be 1 times sine of x. I'm going to be lazy and not put the 1 there. Plus the first times the derivative of whatever the second thing is. So we're going to add x times cosine of x to our first term. So there you have it. There's our derivative. Video's finished. See you later. No, I'm trying to be funny. I don't know if it's working. It's probably not working, but I'm going to keep trying. So we have this derivative, and you might be thinking, how does this help us solve this integral? Well, I see something that looks kind of familiar. I see this, and I see this right here. So your next question should be, hey, how do we go from this point to this point right there? How do we go from taking a part of the derivative that we already know to solving an integral that we don't know? Well, I am so glad you asked. We're going to use some of that information from the first fundamental theorem of calculus to help us out of this bind. So ultimately, we're trying to integrate this. So I want to give myself enough room to put the fancy integral symbol. I always give myself way too much room because I know I'm going to screw up. So the laws of mathematics tell us that whenever we do something to one term, we have to do something to every single term on both sides of the equal sign. Doesn't matter what it is. So for example, we're going to integrate this term. Our variable of integration is x. So we're going to have a differential dx right there. We have to do the same thing to all of our terms. See, I didn't give myself enough room for the differential and the plus sign. I keep telling myself I'll learn, but sometimes it feels like I never will. So we also have to differentiate this as well. And for this part, it is the first fundamental theorem of calculus that tells us that derivatives and integrals are opposites of each other. So that means this here just goes away completely. They cancel each other out. So we can yoink and yoink. It all just vanishes. like magic. So we no longer have an integral on the left side, we just have a simple ordinary function. So we're getting really, really close to the thing we want. We have this, which is an exact copy of the problem that we're given. So the question is, how do we isolate this right here? How do we get rid of the sign, the integral of sine of x dx? And I am, once again, so glad you asked. So it's just some simple subtraction. We're going to take a look at this first equation. We're going to subtract the integral of sine of x. And you might be thinking I'm crazy. Hey, Justin, I thought we could only do that for variables or numbers. I didn't know we could subtract an entire integral. Well, yes, we can, and yes, we shall. It's going to be one of the common techniques we do pretty often in this class. So we have to subtract the same thing from both sides. Once again, I'm going to be lazy. I'm going to, instead of putting it on a new line, I'm going to put it all on the same line. I'm quite dedicated to my laziness. And then this part right here, we have something minus itself. So that part is all going to go away as well. Yoink and yoink. It's going to vanish like magic, which leaves us with exactly the answer we're looking for. So this is what we set out to find, and find it we did. This right here is our answer to the integral of x times cosine of x dx. But I forgot something. Shame on me. Plus c. Got to have that constant of integration whenever we're doing an indefinite integral. So this right here is our true answer to the integral of cosine of x dx. But that's all fine and dandy. But what if we didn't start with the derivative? Originally, we started with this derivative right here. What if we didn't have this to help us? What if we didn't know what the heck derivative we need to start with? Well, we're going to have a more streamlined technique to solve this kind of an integral. So I just kind of showed you the derivation because a lot of my students are really curious about where this stuff comes from. What kind of, we're interested in the way these geniuses come up with these advanced techniques to solve really advanced problems in a simple way. So I want to show you guys a foolproof streamline method to solve something like this using integration by parts. So with the product rule, I want to use the product rule once again to help us understand the formula we're going to be using throughout this class. So let's say we have the derivative of one thing times something else. We're going to use the product rule once again to take the derivative of this product. So it tells us it's going to be the derivative of the first times the second. So the second is here, and then the derivative of the first, I'm going to call that du. Du is the derivative of u. And then it's going to be the first, which is u, times the derivative of the second, which is dv. All right, fantastic. We want to apply integration to this problem yet again. So we're going to integrate all of our terms. And once again, the first fundamental theorem of calculus tells us that derivatives and integrals are opposite. So in the first term, the derivative and the integral are both going to go away, leaving us with simply uv. So let's see exactly what we're trying to do here. So we're trying to solve for u dv. So we can think of this thing right here as being u dv. So what we need to do now is we need to take this entire thing and then move this to the other side, just way up a similar setup to what we had in the previous example. So we're going to do another subtraction. We're going to subtract the integral of v times du from both sides. So integral of v du cancels with negative integral of v du, and I'm going to write the final result. Erase the part that goes away through the subtraction process. I'm going to put uv off to the side, give it a little more, whoa. I hope you guys are at least entertained by me failing on trying to use Zoom. I hope at least I brought that kind of entertainment value to your lives. So we do have our answer now. The integral of u dv is integral of uv minus the, sorry, not the integral, it's going to be just simply uv minus the integral of v times du. Well, that's just fine and dandy, but how the heck do we use that in our problem? So let's take a look at what we have in our problem. We start with this part. In fact, I might rearrange this so that we have this on the left side of the equal sign. really, really OCD tonight about this kind of thing. All right, so this is ultimately what we're going to be focusing on for this lesson. So we have u dv equals u times v minus integral of v du. All right, that's great. But how do we know in our integral, how do we know what's going to be u and how do we know it's going to be dv? Well, it could be anything. We could have this be u and this could be dv, or we could have this part be dv, including the dx, and we'll have this be u. So there's only one way that will work. The hard thing about integration by parts is being really, really strategic about what you choose to be u and what you choose to be dv, because if you don't make the right choice, you're not going to be able to integrate it. You won't be able to use the technique. So now this isn't really something that I was taught in my class, but I really wish it were. It would have made this a lot easier for me to learn. I didn't learn this until I took Calc 2 myself at UNR. And I learned this from a friend. A friend showed me a really, really good way of strategizing what should be u and what should be dv. So the thing I learned is that the thing to pick to be u should always be the thing that gets simpler when you take the derivative. So what are the choices? We have two choices. We have x as our first choice. We have cosine of x for our second choice. So u is either going to be x or u is going to be cosine of x. Let's take the derivatives of both of those things and then see what would be a good candidate to be u. So the derivative, I'm going to start with x. The derivative of x is 1. The derivative of 1 is 0. The derivative of 0 is 0. And then we'll just continue being 0. We've already broken it down to the ultimate, most simple derivative. So I want to do the exact same thing with cosine of x. I'm going to take the derivative of cosine of x. That's going to be, of course, negative sine of x. And then I'm going to take the derivative of negative sine of x. That's going to get us negative cosine of x. And then the derivative of negative cosine of x is going to be negative sine of x, which is really just positive sine of x. And then we're going to do one more derivative. We're going to take the derivative of sine of x, which gets us cosine of x. So notice how we ended up at the exact thing we started with. We started at cosine of x, and we ended with cosine of x. Notice how this thing does not get simpler the more we take the derivative. It just cycles further and further through similar terms until we end up what we started with. So this is not a very good choice for u. This does not get simpler when we take the derivative, so we don't want that to be u, which means we want this to be u. So x is going to be u. Naturally, that leaves everything else to be dv. And we want to include the differential in our dv as well. We always include the differential in dv. The dx is never going to be part of u. So we have our u and we have our dv. Life is good. So we're going to do something similar to what we do for u substitution. Off to the side, we're going to write out our definitions for u and dv. So u is equal to x. dv is equal to cosine of x times dx. So next, if we look at our formula, it tells us we're going to need a du and we're going to need a v. We don't have any of those things yet, but they're pretty easy to find. Let's start by finding du. Du is going to simply be the derivative of u. So du dx, the derivative of u with respect to x, derivative of x is just going to be 1. And what I'm going to do now is I'm going to take this differential equation right here. I'm going to multiply both sides by dx, which gets us the following. It gets us du is equal to dx. Nice and simple. But then how the heck do we get v? So du is pretty simple. All we need to do is take the derivative to get du from u. But we need to go backwards. If we're trying to get v from dv, we don't need to take the derivative. We're actually going to take the antiderivative. We're going to take the antiderivative of cosine of x dx. That would be sine of x. Fantastic. So we have all the information we need. Now we're going to do some substitution. So we're going to have two terms. Our first term is going to be u times v. And I like color coding things. It just makes it easier for the brain to make connection between pieces of information. You don't have to do it if you don't want to, but you might find it helps a lot. All my notebooks look like rainbows because of the multicolor highlighters I use. Just really helps my studying have so much more clarity. I make much better connections with the information much better when I have things color coded. Give it a try. You might like it. Oops, forgot some things. It doesn't help too much if you're colorblind like me, but I'm still able to discern the different colors. Like I wouldn't be able to discern between blue and purple very well. So I usually just stick with the primary colors. All right, so now let's go ahead and make the substitution. So we have u times v coming up first. So we can see that u right here is x, and we can see that v right here is sine of x. So that means uv is going to be x times the sine of x. And then the next part of the formula tells us we're going to subtract the integral of v times du. So we're going to do the integral v, that's in blue, that's sine of x. And then we have du, that's in yellow, that is dx. So by this point, you might think I made a mistake because we still have an integral. Hey, Justin, we're trying to find the integral. How come we still have this integral symbol there? How come we still have more calculus to do? I thought we were finished. What gives? Well, we haven't completely finished the integration process, but what we did is made the integral much, much simpler. So at the very beginning, we were given this. We had no idea what to do here, but we're able to break it down into two smaller things that we know exactly what to do with. And that's a concept called modularity. It's something that it applies a lot in computer science, computer programming and coding specifically. Modularity is the process of breaking up a really big, scary, complicated problem into small, manageable pieces. That's modularity. And that's something that comes up quite a bit in not only computer science, but math and physics and even chemistry. So modularity is a really powerful tool and highly useful. So that's what's being employed here. We're taking this integral we had no idea what to do with. We're breaking it up into two smaller pieces that we do know what to do with. So this part right here, we don't need to do anything with that whatsoever. There's no more calculus to be done with this part in the box. No more derivatives, no more integrals. But notice how we do have to integrate this part now. We do know how to integrate exactly this. The antiderivative of sine is going to be negative cosine. So the first part's going to remain the same, x times the sine of x minus, and then this is going to be minus negative cosine. So minus negative cosine is going to turn into positive cosine of x. And then we need that constant of integration. We need that plus c. So that's how we do it. This is our complete solution to the integral of x times cosine of x. Let's try a few more examples. So what if we're trying to integrate the function natural log of x? We need integration by parts to help us with this one. It doesn't even really look like it because with the last one, we're used to having an integral of one function times something else. We had x cosine of x for the last one. This one doesn't really seem like it follows the same format. It's just one thing. But we really do need integration by parts for this, and I'll show you why. So we don't know initially what this antiderivative is. By this point in the class, we don't know how to find the antiderivative of natural log of x, which means it's not a good choice of dv, which means it's going to have to be u. So we're always going to have a u and a dv. So I think I'm going to put the formula back up there just to use as a guide. This is the derivation of the product rule for derivatives. That's what integration by parts is based on. So we have a u and we have a dv. So let's find du. Du is the derivative of u. So that's going to be 1 over x times dx. And now let's find v, the antiderivative of dx. Well, we can think of dv as being 1 dx. And when we take the antiderivative of 1, we get x. So we have everything we need. We have u, we have dv, we have v, and we have du. So now let's do uv. I'm not going to color code this one because it doesn't really fit the right format for that kind of a thing. So I'm going to just leave that be for this particular problem. So we're going to set that equal to uv minus the integral of v times du. So we're going to have uv. So u is going to be natural log of x. And then v is going to be x. I'm going to put the x before because I'm picky. So it's going to be that minus the integral of v times du. So v is x, du is dx over x. So we have an x on top that cancels out nicely with the x on the bottom. There is no satisfying way to cross out an x. It always bothers me. Maybe if I embellish it a little bit. Have you guys found that out? Do you guys kind of agree that there's no satisfying way to cross out an x? Well, I guess this kind of works. It kind of satisfies my OCD a little bit, mildly. So now we no longer have any x upstairs or downstairs. All we have is simply minus the integral of dx, and we know exactly what to do. So we're going to do x natural log of x minus the antiderivative of dx, which is just going to be x. Let's see. Bam. There, we're done with that one. So I invite you to, if you're doing these types of problems on your own, I invite you to take the derivative and see if you get the same answer you're looking for. See if we get exactly the function we started with. You should take the derivative of this, and we know we did it right if we get natural log of x for our answer. Let's try a bit of a complicated one. You know what? Actually, I think I'm going to save this one for the next video. So there's going to be a next video where we try maybe some more complicated integration by parts problems. I think we're going to do maybe one more simple one in this class. Let's try t times e to the negative t dt. So we have the integral of u dv is equal to uv minus the integral of v times du. So remember, we always start an integration by parts problem by deciding which function would be a really good candidate for u. Excuse me. So remember that we always want u to be the function that gets simpler when we take the derivative. We have two choices. We have t, we have e to the minus t. Take some derivatives and see what would be a good candidate for u. So the derivative of t is 1. The derivative of 1 is 0. I don't know why I put that line through the 0 sometimes. No good reason for that. Now let's take some derivatives of our other function in the integral, e to the negative t. When we take the derivative of e to the negative t, we get negative e to the negative t. If we take the derivative of negative e to the negative t, we get negative e to the negative t, which is just e to the positive t, which is exactly what we started with. So these two are going to just keep repeating. That's the weirdest shape I think I've ever made. So these two right here are going to continue to repeat. This function does not get simpler when we take the derivative, which means e to the negative t is not a very good choice for u, which means this is going to have to be u. This right here, including the differential, is going to have to be dt. So just for the sake of my OCD, I'm going to change the variables and make them proper. T's instead of x's. If I put this much effort into my financial planning, I probably wouldn't be in 5 figures of student loan debt right now. So we have our u, we have our dt. What we don't have is our du and our t. So if dt is e to the negative t, we're going to take the antiderivative of dt to get just t. So we're going to take the antiderivative of this. We're going to work backwards. So the antiderivative is positive e to the negative t. And we have everything so far except du. Du is going to be the derivative of t, which is just dt. All right, fantastic. So now we're going to plug things in and continue. So u times t is going to be t times e to the minus t minus the integral of t times du. So t is e to the minus t. Du is going to be dt. So it's already looking a lot simpler. We don't need this anymore. So we're going to make this t e to the minus t. And we're going to subtract the antiderivative of e to the minus t. So if the antiderivative of e to the t is e to the t, that means that the antiderivative of e to the negative t is going to be negative e to the negative t. So a negative times a negative makes a positive. So we have our solution is going to be this. We have the antiderivative of t times e to the minus t dt is going to be t times e to the minus t plus e to the minus t plus c. All right, there you have it, folks. That is how integration by parts works. So keep an eye out for the next video. We're going to be going over some more tricky, more advanced integration by parts problems. See you in the next video.